just let me know if you have any question. We are not in the exam, so we have some time to ponder and think about the result and see if it's intuitive or not. So what do we mean by QNC theta? Like I said, QNC is non-conservative loads. So this is the part that affects the theta motion in the direction of the theta, right? So theta is a rotation about this point, correct? So what do you think about the loads affecting the theta motion? What kind of loads will be? The what? Yeah, say again.
It's positive, so it's making it rotate faster.
Yes, what kind of loads will be?
Perpendicular to
Moments?
Moments about this point, right? Moments about this point will cause rotation about that point, the same point, right? So actually QNC theta represent the moment about this guy. It's Q, this is theta, this is Q sine theta, right? So Q sine theta times L, here is the first term. Is the moment about theta. And the same here, we have P cosine and P sine. So P cosine times all this guy. P cosine, phi plus theta times, I mean, this is a little bit, you need to do it carefully because this guy doesn't pass through theta. So actually I need to do it carefully, okay? And here is a way to do it for you. So this is why the expression is not the same. So if you're smart, you can do it using Newtonian mechanics. I know that the QNC theta will be the moment about that point due to all the loads. The one due to Q is easy, the one due to P is a little bit tricky. You need to do just the resolution correct. Here is a constructive way turning the crank to do it. Any question? So now we are expert on constructing the left-hand side of Lagrange's equation. Very easy, from a single scalar function. And whenever we have a damn non-conservative load, we know now how to deal with it. Because there is that always common rumor about Lagrangian mechanics that it's only valid for conservative loads. No. You can deal with whatever problem. Just give me the problem. Here is a way to solve it. So for the non-conservative loads, here's how we deal with it. Okay? Constraints, typically ignore them so far, but if you like not to ignore them, I will give you a means how to account for them, if you like. Okay? Any question? This is definitely easier than Newtonian mechanics. And like I said, ironically, we typically teach Newtonian mechanics to the undergrad and Lagrangian mechanics to the grad. Yes?
Are there problems that you only use Newtonian mechanics to solve that you can't use Lagrangian mechanics?
Say it again, please.
Is there any problems that you only use Newtonian mechanics to solve?
Can be.
Yes. If there would be a force P applied also in the mass 1, the force non-conservative one would be Q and P.
Yeah,
In different directions, but
that's fine.
Q and P.
You add it.
Yeah, so you add it there.
You mean I need to add it now or what?
No.
If there is a
If
force,
there is another force
P,
P here,
then your F non-conservative 1 will not only be Q in the J direction, it will be P in the I plus Q in the J. Yes.
How to approach this if there is a moment acting on the point of contact, like
For particle masses, the moments are of no concern. But for rigid bodies, because we don't apply moments on a particle mass, we apply moments to rigid bodies. We did not, and this is good to bring. So far in the Lagrangian mechanics, in 3 lectures that we have been dealing with, we did not introduce how to deal with rigid body yet because simply your kinetic energy actually is not complete. Remember, kinetic energy is 1/2 mv squared for a particle. For the rigid body, it's not only 1/2 m velocity of the center of mass squared because you have a lot of points. Okay, it's not only that, there is another term. So we did not know yet how to deal with rigid bodies within the framework of Lagrangian mechanics. Later we're going to do for sure. Any question? Yes, Ivan?
Probably said that, but what happened with the third equation?
Yeah, I mean, I'm not going to continue, but the third equation you're going to do it, yes. Yeah, it's the exact same thing. So yeah, we're done here. We're gonna introduce constraints in detail. Any question, please? Please, if you have any question. By the way, just also to motivate you more, the final will not have anything from before. So if you lost the big term, if you lost everything, that's perfectly fine. Now you have the final, and you can start from this lecture. Okay? So if you really have anything, don't let it pass. So I was a student not long time ago, and like anybody, I like to play in these lectures. But then when I come and regret, I was hoping that the teacher says something like, "Oh, you know what? This is not dependent on something before." So that I just pay more attention to it. I was just thinking that, oh, this is clear to everybody, and because I missed these two lectures, I should not know anything. This is not the reality. Okay, constraints. Like classification, right? Holonomic constraints and non-holonomic constraints. A lot of funky words: monogenic, polygenic, holonomic, non-holonomic. So, holonomic constraints, meaning that there is an explicit relation between the Q's. So you have psi, some function of all the Q's is equal to 0, representing your constraint. It's like, the pendulum. The pendulum, we have a mass in the plane, so in general we have 2 degrees of freedom, subject to one constraint. What's that constraint of the pendulum? How do you write it if the 2 degrees of freedom are x and y for the particle? What's the constraint? X squared plus y squared equals length squared of the pendulum, right? So x squared plus y squared equals L squared. Simply get L squared to the left hand side, please, to make it a 0 equation. So you have a relation, a 0 relation between all your coordinates, okay? Whenever you can write an explicit relation, because there's sometimes we have constraints that you cannot represent them simply by a relation between the coordinates. Whenever we're going to talk about them, these are the non-holonomic constraints. I'll give you some examples for that. But first, let's deal with the easy ones. Holonomic constraints are the ones that you can write an explicit relation between the coordinates. A pendulum, or this guy, a mass that is rolling over that surface, and this surface actually maybe a parabola in the plane. So this is x and y for the mass, and this shape of the curve is y equals function of x. So your psi is simply y minus f of x is 0, right? Whenever you can write an explicit relation between your coordinates x and y, or in the pendulum also x and y, so in general it's psi as a function of all the q's equals 0, then this is a holonomic constraint. Okay? Any question about that? We call this holonomic constraint. And for holonomic constraints, we have, let's see. For the holonomic constraint, we have one of two options. So in the pendulum, I have 2 degrees of freedom subject to one constraint. Or in general, I might have a problem that is 5 degrees of freedom subject to 2 holonomic constraints. The holonomic constraints, like you see here, they are easy ones in the sense that you can, from this equation, can get one of the degrees of freedom in terms of the other. And just whenever you see this degree of freedom, whenever you see y in your problem, just replace it in terms of f of x. So everything was in y, now is in terms of x. You got completely rid of y. Okay? So holonomic constraints allows you to get rid of degrees of freedom. And this is what we're actually doing within the framework of Lagrangian mechanics. We typically ignore the constraint and get rid of one of the degrees of freedom, and that's it. We're happy. So if you have 5 degrees of freedom subject to 2 constraints, then, or 5 coordinates, let's be precise, 5 coordinates subject to 2 constraints, then you can just use these 2 constraints to get rid of 2 of the coordinates and live with 3 degrees of freedom. Okay? So you can do eliminate, use, constraint to eliminate some Q's. This is what we have been doing.